Well, I think we'll make a start. Hello and welcome to the third webinar in the series of Stormwater 360 webinars this year. It is a great pleasure to have Mike Hanna join us and to present to us on GPTs, Gross Pollutant Traps, their performance, their approvals, and how to evaluate the GPT and how to put it in and design it into your network. A couple of housekeeping things. We are recording the meeting, so there will be a recording available afterwards to watch if you would like. If you have any questions at any time, please do put them into the meeting chat. What we'll do is at the end of the session, we'll have a question and answer session. And I'll collate the questions together. So if there's any questions that are on similar themes, then we'll be able to answer those and talk to those. So gross pollutant traps, their regulation, performance, and evaluation. It's an interesting topic and certainly one that I've learned a fair bit about working with Mike, putting together this webinar for you. I'm Matthew Howes. I'm a sales associate in the sales team within Stormwater 360, and we deal a lot with all sorts of stakeholders, whether it's councils, design engineers, contractors, asset owners, and maintenance providers around the design and implementation of stormwater treatment devices across New Zealand. We have within Stormwater 360, we have a sales team, but we're very, very fortunate to have world-leading expertise in-house. And it's fantastic that we have Mike Hanna, who is our co-founder and technical director at Stormwater 360, to present to us today on gross pollutant traps. Mike founded Stormwater 360 in 1996. Sorry, not 1996, Mike. Yeah, 1996. And has been at the forefront of stormwater and stormwater management ever since really the inception of water quality management, both in America and in New Zealand. He was the 2021 New Zealand Stormwater Professional of the Year and is ex-chairman of the Water New Zealand Stormwater Group. Mike sits on a number of boards: the National Municipal Stormwater Alliance in the USA, the National Center for Stormwater Testing and Evaluation from Products, Practices and Leadership Group in the USA, and the ASTM Committee in Stormwater Control Measures in the USA. ASTM is a group that is writing testing protocols for new and emerging products, stormwater management products in the States. Mike is a member of the American Society of Engineers, Engineering New Zealand, is in the Water and Environment Association for Ontario in Canada, and sits and advises on the Stormwater Industry Group in Australia and the International Water Association. So from I don't really think there's anyone in New Zealand that is going to be better qualified to speak to us about the performance of gross pollutant traps and how they're applied and the technologies applied overseas. So looking at the webinar itself, a little bit about us, Stormwater 360 and Enviropod, and then we're going to look at trying to define what a gross pollutant is and what a gross pollutant trap is. We'll look to regulations for both gross pollutant traps and removal of gross pollutants, both domestically and internationally. We'll look at the performance of gross pollutant traps. How do they achieve what they're setting out to do? And by what methods can we remove gross pollutants? And then we'll draw this all together with a section on evaluation. So engineering judgment for when you're choosing and specifying a gross pollutant trap, verification and certification databases, maintenance of safety, and some thoughts about whole of life costings when it comes to choosing gross pollutant traps. So a little bit of background on Stormwater 360. Started in 1996, and I don't know if you can see here, This is actually a photo of Mike from way back when. I'm thinking he should bring back that hairdo. Fresh out of university, and saw all of this litter and trash going into the drains, washing through and out into the Waitemata Harbour, and thought there has to be something that we can do. And with TP10 only recently being released, we were still very new to this. Everyone was still very new to understanding. But as both Stormwater 360 and the industry has learned more and more about stormwater management and the water quality, research, development, and innovation has then been at the core of our business. It's not enough for us to say, this is what we have, go away and make it work. It's really important to us that we understand stormwater and we understand what is going on. We've invested in Enviropod to provide an accessible solution to stop plastic being transported from the land to the world's lakes, oceans, and rivers. So across New Zealand, Australia, the USA, and Canada, there are over 50,000 installations. And that's quite a large scope of projects to work on, and regulations to look at and adhere to. We expanded to Australia recently, very active in Australia. We've established Enviropod in Canada. We've worked with both the public and private sectors in Ontario, Calgary, British Columbia, and the Maritimes. And we've continued this trend down into the United States of America with installations in Portland, Oregon, Foster City in San Francisco, and California. So a little bit about then the products that we have installed in these applications. Mike is going to give us a very much a technical overview and a high-level overview of these products, but it's important to place them in context for what you might be able to specify and what you might see in the ground. There's two real sorts of gross pollutant traps, and the first is gross pollutant traps that are placed at source. At source management is always a great outcome for stormwater treatment, and we have three options because not every site is going to be suited to a single option for at source gross pollutant traps. So we have the original, the Enviropod, the high performance catch pit insert with a 200 micron liner. We have the Evolution, the litter trap, which is a 5mm trash capture with a hand maintainable basket. And then coming online in 2023, I'm reliably informed by Mike, but currently going through testing and it's ETV verified out of Canada, is an at-source trash and sediment capture device. However, for large catchments, even mid-sized catchments to large catchments, where there's a number of contributing catch pits, using an inline or end-of-line gross pollutant trap is a fantastic option. And we have three products that fit within that category. The first is the Vort Capture, which is a screening GPT that has tunable sediment removal performance. The Vortex is a separation gross pollutant trap that is very capable of handling high flows. And the Cascade Separator, again, is a separating gross pollutant trap that runs very high performance, and it's an economical manhole gross pollutant trap. The reason for having three of those is not every site will need a screening GPT. Not every site has the depth available for a manhole device. So the Vortex is quite shallow at 2 meters. And not every site has the footprint available for the Vortex. So the Cascade, being in a very small manhole, provides a great outcome there. You'll see these products referenced throughout the presentation, both from testing and their integration into networks. If there's any questions about those products, please do drop us an email and we'll happily come and have a chat to you. Mike said that he'll buy you lunch, so and we can talk about that further. But for now, thank you very much, and great to hand over to Mike to talk further about gross pollutants.
Thanks, Matt. Just taking control, and I'll just make sure I can get the pointer. Yep, that works fine. Cool. All right, gross pollutants and gross pollutant traps. How do I advance? That's the next thing. Here we go. So let's define them. Was originally, the whole term gross pollutant traps came out of Australia. Well, back basically when TP10 came out, late 80s, early 90s, and they just decided to define it as what could be retained on a 5mm screen. So it was a pretty arbitrary thing, but that was considered a gross pollutant or a macro pollutant. Roughly that consisted of litter, trash and debris, leaf matter or box or anything kind of large as a debris. It also included coarse sediments, but a lot of coarse sediments actually will slip through a 5mm screen. Now we've done a lot of work over the years of nearly 30 years analysing what we capture in our gross pollutant traps, whether it would be an enviropod or a vort capture or a cascade. And roughly, and we also have looked to a lot of the research. A lot of the earlier research was done out of Australia, but there's now a considerable amount of research being done out of the USA and in Canada and even Malaysia. And so when you capture gross pollutants, we find there's between 50 and 90% is actually organic material, the leaf material. And that's kind of shown in this picture. You get this kind of a mess of plastic and organics and sediment all kind of bound up in one. We also found that only 20% of that material is actually kind of floating, or less than 20 is actually floating on the surface. A lot of it sits in the water column, and I'll talk a bit more about that later. And I haven't converted these. That's pounds per acre. I can't do that conversion off my top of the head. I've used the slide somewhere else. But that's kind of the loading. We're looking at roughly around about, I recall now, it's roughly about 250 kg per hectare of gross pollutants coming off. And that's often off a catchment. And that's not often actually factored into your stormwater design. We think about the load of suspended solids, but we don't actually think about what that gross pollutant is going to do and end up inside our device. Another thing about that metric, kg per hectare per year, that's actually not that good a way to quantify gross pollutants because they are quite often very light. Like plastic is extremely light, leaves are extremely light, and that actually makes them, or less, not very dense. That makes them quite a significant volume. And I can't do that conversion in my head, but I will come back to when we send out this presentation. And what that means is a per hectare of volume of mass that's coming down and ending up inside your treatment devices or in the receiving environment, because a large volume of material will be very visually unattractive. So I've got a couple of little videos running here, and the picture here is what we kind of gross pollutants we capture once we've taken the organic material out. There's a little bit there. And here's a pit, and you can see it's a lot of like wrappers and plastic films. There's often, like a pen might get broken over and little bits of hard plastic. And what we consider is, what we like to remind people is that plastic doesn't float on the surface. It actually has a density of about 1 or slightly under or slightly over. And that video at the top, which I was just quickly showing you of the material that we're taking out, I might just jump back there if possible. No, I can't. That material there was in the stomach of a turtle that they found washed up on the beaches outside of Auckland. That's from Auckland Zoo. I can't seem to turn that on, Matt, but hopefully it will. But really the point I'm trying to say here is that the material that we're catching in our gross pollutant traps is the same as what they're finding in the stomach of turtles. And that's really the big driver for me. It floats in the water column like in the video here, and marine life tends to think it's food and eat it. And we've all seen pictures of the turtle that ended up with a straw in its nose. And also the fact on the damage on whales and other marine life is significant. In fact, every turtle they find washed up dead on New Zealand beaches has plastic in its stomach. That's what the Auckland Zoo is reporting. So if we're going to use a gross pollutant trap to capture this kind of this gross pollutants, what do they actually kind of do? Well, they have various names around the world. Like we're here in New Zealand, we call it a gross pollutant trap, and we borrowed that from the Australians. Originally, the Australians call a gross pollutant trap a separator with a screen in it. We don't seem to make that definition or demarcation in New Zealand. We just call anything that's a kind of a pre-treatment device a gross pollutant trap. They're called hydrodynamic separators in the US. That's the separating ones, but they call them screening separators or settling separators. And they're also called oil and grit separators in Canada. In California, they've actually changed the definition a bit, and they are now calling them full capture devices for the capture of trash, and they require a screen. So they've separated out the sediment from the true gross pollutant, i.e. that material over 5 millimeters in size. And as I said, they capture a whole bunch of sediment as well as the trash and debris, and some of them actually can be designed to capture hydrocarbons, and that's more from on a spill basis, not necessarily like a coalescing plate separator, but more like an API separator. So they can kind of do a good starting job on oils and free oils. So if someone was to pour oil down the catch basin or catch pit, it's likely to be caught in a GPT that's designed to capture oils as well. I really see them as a pre-treatment device. I don't really see them as a standalone device that you'd use as ultimate stormwater treatment, but they have a lot of benefit in that, and they're used especially in overseas and New Zealand as a pre-treatment for infiltration or soakage, or pre-treatment to green infrastructure. The pictures here I've got is here's in New Jersey. You do not need to place have a forebay in your pond. You can put a hydrodynamic separator instead, saving roughly about 50% of the land, 15% of the land. This picture up there is pre-treatment to a detention tank. But, you know, once you get material into a detention tank or a soakage system, it's very hard to get out, and it really limits the capacity of those systems. Really, gross pollutant traps are good to use because they have a small footprint, and they can convey quite a large amount of flow through them. They have minimal head loss, especially when they're placed offline. Online, they can have a high head loss if high peak flows are going through them. And they really make a visual difference on the receiving water body. And that's really important. You know, the public don't like to see trash and plastics all through their green infrastructure. And we definitely don't like to see it in our waterways and in our beaches. Also, the real benefit of can't turn that sound off. The real benefit is in a treatment train. And the picture on the video on the right is a vort capture. Vort capture is a vortex separator that makes water go round and round and round, and has a non-blinding screen. Now I put this picture in here because hopefully that'll stop making noise soon. Because we used to work with Auckland motorways and design treatment systems for the high anticipated load that they were going to get off the motorways. The more traffic movement there is, can you stop that noise? Stop the sound. The more, sorry, I lost my flow there. The more traffic there is, the more sediment there is coming off an area. And so we were working with them and over-designing the systems just with the amount of sediment on the motorways. Then we we put one of these vault captures in as a bit of a pilot. And we did the life cycle cost analysis by putting a vault capture up front, which could be vectored out every 6 months. It was more cost effective than putting extra cartridges in that needed media replacement, and that would have to be replaced every 18 months. We found by putting a vault capture in up front, we could reduce the amount of cartridges and also extend the longevity of maintenance frequencies. Also, another advantage is that it actually improves the performance when you have 2 stages in a treatment train. And in Australia, we're doing a lot of work with putting Enviropods up front of filters. And when we model in the music software that they use to design systems in Australia, we find you get an improved performance by using 2 treatment devices in series. I'm going to move on from that because it's very annoying. If you want any more information about those 2 studies, just sing out to us afterwards and I can help. We can supply that information. Sorry about that, but let's talk about now gross pollutants and their regulation. Well, in New Zealand, we don't really regulate gross pollutants. In fact, the very first TP10 said, litter, trash, it's not really a problem. It's just an aesthetic issue, it's not a problem at all. Fast forward, 20, 30 years now, and we know that millions of marine creatures have died from gross pollutants being discharged through stormwater into our receiving water bodies. So there's been no regulations in the past until recently, when Healthy Waters and their Network Discharge Consent decided, hold it, there's some areas where we see a lot of gross pollutants, and they're often where you store waste storage or where you put your rubbish bins or loading zones. So they regulated under the NDC and the bylaw that these areas now need gross pollutant traps. I also, while they don't necessarily talk about specifically addressing gross pollutants, Auckland's now moved to a best management practice approach where they want to see the best solution being put forward for the catchment and their consenting. And so a treatment train is really lends to that idea because you're going to get enhanced performance and you're also going to lower the maintenance costs and the operational costs by playing a treatment train. So a treatment train, if we are trying to put best management forward, should always be the offering when you come up with a stormwater management plan, some sort of treatment train. That picture on the previous slide was from the original first TP10. That's probably changed a lot. We could probably talk about more like pre-treatment, treatment, and then retention or infiltration, because really that's the missing link in a treatment train, is trying to reduce the volumes of stormwater running off. Now, in these in the NDC and the bylaw and Auckland Council, they refer to a GPT guidance document called TR 2011-006. Now, that document really is more of an overview document. It doesn't give you any idea about how to design the systems, what the hydraulics are, and how they work, etc. And I'm hoping I can fill some of those gaps with this presentation today. Also, as we travel around New Zealand, there's other regulations relating to gross pollutant management. And Christchurch in their water and wetlands guide, they have this little diagram here and there, which is the suggested way of managing stormwater with a treatment train. And they have what they call a macro pollutant trap, something that captures 5 millimeters and over. Then they ask for a pre-treatment swale for the sediment, for the coarser sediment, and then it goes into their first flush basin and into a soakage chamber. In this example, there's a range. But really, gross pollutant discharge should be regulated in New Zealand, because under the Resource Management Act and the section on discharges, you're not allowed to discharge anything into stormwater. And some of the work we've been doing around New Zealand with litter trap, on average, we see 1,000 pieces of litter being trapped in the litter traps for every catch basin we put one in. And so there is plastics and trash and gross pollutants being discharged constantly through existing networks. And that kind of contravenes what the Resource Management Act is saying. And that also flows down into the freshwater and the coastal policy statements. Pretty much we can't be discharging or doing anything that's harmful to those water bodies. And we know gross pollutants and the plastic associated in them is having a detrimental effect. And even Te Manawatū actually has gross pollutants have a relationship with that, because I don't think we're really engaging with Māori enough and talking to them about this problem of gross pollutants we have. And we need to, because I'm sure if we are trying to protect the life force of our waterway, we need to address it. Overseas, they're getting a bit more serious with their regulation around gross pollutants. As I mentioned, California has been the first municipality or region to bring out very strict regulations around trash and gross pollutants. It is they've gone to all the existing stormwater permits in California, both city councils and counties, as well as private businesses and the transportation organization. And they said, well, we know this is a problem now. Your current plans, your current permits don't address this problem. So you've got 10 years to come up with a way and implement a way of managing trash to be conforming with your existing permits. So that's really created quite an industry in California about dealing with trash. And there is real visual difference being achieved as cities and municipalities are moving around and retrofitting trash capture mechanisms. It's not all about also putting in treatment devices. There is a pathway for using softer engineering, such as education and street sweeping, also to meet the regulatory requirements. But they've made it compulsory to deal with trash. In New Jersey, they allow pre-treatment devices, as I said, in front of green infrastructure. New Jersey has moved forward that they only accept the state of New Jersey only accept green infrastructure, but they encourage pre-treatment devices that have gone through their certification and testing program. The same as in Washington, they may have a requirement to pre-treat any sort of infiltration, any sort of soakage. And that really makes sense. You know, you can get contamination of the aquifer, you can get clogging of the stormwater asset if you're trying to dispose of water under the ground. And really that just makes sense to make sure that you have a pre-treatment device. Also, Washington has a testing protocol that certifies these devices, so people can purchase with a bit of trust that it works. In Australia, they don't really prescribe pre-treatment devices. They typically use a modelling approach to achieve their stormwater outcomes. They have a modelling system called MUSIC, which is quite good. It really focuses on sediment, nitrogen, and phosphorus. But when you are actually designing with MUSIC, you'll find that if you can place a pre-treatment device in there, you often can make your bioretention system smaller, or that's the only way you'll actually get to the regulations, because they have quite strict regulations, especially around nitrogen. It's a really hard thing to achieve. In Canada, again, there's requirements in certain municipalities for pre-treatment to all infiltration and also to green infrastructure. We're using Envirobase and Litter Trap pre-treating SIVA cells where you're in streets, where they want to put streets in the urban areas to reduce urban heat island effect and also intercept the rainfall, just the urban forest sort of thing. And they want to use the stormwater to irrigate it, but you've got to get the plastic and the debris out, as well as trying to get a lot of the sediment out. So there's a requirement in Canada and certain municipalities to apply pre-treatment. And so all of this regulation around the place has created a whole bunch of testing programs, and there's quite a few there now around the world. I've just mentioned a few. I mentioned New Jersey, and I mentioned the Washington Department of Ecology. We also have Canada uses the ETV approval process, and as Matt said, we've got our new technology, the Envirobasin, approved and certified under that approval system. And then there's a whole bunch of other states in the USA have been developing testing protocols. So what we also have, the Germans and British have also developed testing protocols. And they're all these protocols are all slightly different. For example, the state of Washington requires field testing. However, the British and the German ones and the New Jersey system, they only require a lab test. So, you know, it is often, they're not all the same. They have different kind of focuses, such as like Stormwater Australia, that requires field testing. But they don't really worry too much of the flows. They've got what flow rate a device works at. Where the Department of Ecology is that you really need to prove that it's meeting your targets at the flow rate you say is the treatable flow rate. So what's happening in the US at the moment, and I'm a member of it, is that they've created this organisation called STEP, the Stormwater Testing and Evaluation of Products and Practices Group, and that's part of the National Municipal Stormwater Alliance. And they're developing a system that's going to unify all of the USA and hopefully Canada and create one standard way or two standard ways. There's going to be a field testing protocol and a lab testing protocol, and it's going to standardize it. And like any standards, they've actually gone to ASTM, the American Standards of Testing and Materials, and they're creating it. And that's an international standard. Anyone can be involved with it. And I actually sit on these committees as well. And they're quite interesting to work on because you have to get consensus in order to come up with a standard. And so we've got all different people, city councils, and ecologists, and suppliers, all working together to try to get the best standard that you can get that's fair and reasonable and mean we can move forward and evaluating these things all in the same way. So I'm hoping that once these standards are produced, that we can maybe talk to the New Zealand standards people or the Australian standards people and try to get the whole world on the one testing protocol. Because, well, testing doesn't mean that's what you're going to get on your site. It is a good way to just benchmark performance of these devices, so you have some confidence when you put them in. So moving on to the next section, we're going to talk a bit about the different sort of treatment mechanisms inside gross pollutant traps. And I really kind of split it up into two. You know, I did talk about the trash and the fact that plastic in the trash is neutrally buoyant. It sits in the water column like the diver swimming in Bali. It doesn't float on the surface. And the only way you can really remove that is by a physical screen. So that's one type. The other type we're going to talk about is more separation, and that's about settling out of sediments. And also separation can be used for removing hydrocarbons. So when we're talking about screening, there's two types of screening. There's direct screening and there's indirect screening. Now, direct screening is where you, say, put a screen in the pipe or across the outlet. And what happens with direct screening is that the water is flying straight and all the debris is flying straight into the screen. And that really causes it easily to blind up and clog up, such as you can see in this picture here of a screen placed over an outlet. So what advancements in screening technology discovered, and this is quite back in the 80s, is that if you indirect screen, you're less likely to get things blinding, your screen's blinding. And indirect screening means the direction of the flow is in a different direction to the screen. So swell separators apply this. So here's a vort capture. The water comes in here and spins round in this part of the device, and this is the screen across here. So by creating a vortex going round and round and round, the screen self-cleans as the water goes around. The water then pops up out of this orifice and then goes out the outlet pipe. We also see this in catch basin devices that use baskets or bags. What happens is the water flows in and is flowing down, yet the screen is perpendicular to it. And all the material that gets trapped on the screen washes to the bottom, as you can see in this Enviropod from Brisbane City Council many years ago. So really, you want to check out a gross pollutant trap with a screen and make sure it's indirect screening. You also want to think about the loading rate. And when I mean screen loading rate, that's how much flow is going over the screen. So if you had say we've got two screens, one's this size, so let's say that's 10 meters squared, and this one is, say, like 2 meters squared, and you put the same flow through them, it's more likely that the small screen is going to clog up. It's not really rocket science because it has a higher loading rate. There's more water and debris going through a smaller area, so it's more likely to clog up. Now, this also applies when we think about where we're placing devices in a catchment. Now, if we were going to go to the end of the line, where and these devices at the top have had a lot of press coverage lately, but this screen here is not really big compared to the catchment that's feeding into it. Like, this device is probably taking a peak flow of about 300, 400 litres a second. Where if we go back to a catch pit, which only has a maximum flow of 20 litres a second, you have quite a lot of screen area relative to the flow. So here's a little thought. When you're looking at a device and you're looking at a range of devices, just have a look at the screen area of each of those devices and just think about how much water is likely to come into that. Because if it has a low screen to flow ratio, it's probably going to clog pretty quickly. Now we're diving a bit into the hydraulics, and this is really important because screens have a head loss, and you need to make water well up behind the screen to give it the force, the energy to push it through a screen. And this is a kind of simple definition of what head loss would be. We have a water flowing down through here. It has to well up to push the water through the screen, and it comes out at a lower head. And that difference between water level, that's what we defined as head loss. Now, in a basket or in a basket situation, as an example, if we had a low head loss screen, well, the water's not going to well up much in the basket. But if we had a high head loss screen, well, it's going to well up significantly and might go into a bypass, and therefore it's not treating what we want it to treat. We have a criteria, say, to treat a 10mm storm. Well, if it's welling up because of a low head loss fabric and going into bypass, well, we're not going to be treating that. And we're likely also to lose some of the material we've trapped. Same way if we were putting a screen across a pipe, we really need to know that head loss because it might well up and go into bypass and cause flooding even potentially. So all of this is being addressed. There's a new ASTM standard for testing trash devices, and the hydraulics is a really big part of it. And that's the number if you want to go onto the ASTM website and have a look. Also, the type of screen you're using will really have an influence on the head loss. Now, I've got two screens here. Screen B has roughly about 450mm holes, where screen A has 200mm holes. Now, you'd think, wow, screen B's got bigger holes, it'll have less head loss. But unfortunately, that's not true. See, this is the head loss for the two screens, and this is the amount of head loss for different flow rates. And you can see B has significantly more head loss. So the factors that really are influencing it is the amount of open area in that screen. You can see that one's got a lot more. And also the shape of that screen, because this is really non-uniform, not clean shapes, and that has more drag than, say, screen A. So your shape and your open area and your dimensions of your screen influence the head loss. So as I mentioned, that trash standard, now this is being developed because there's regulations now that you must capture 100% of 5mm particles or larger in California. And these trash regulations are also spreading across the state. So the ASTM has set some pretty detailed testing requirements for testing trash capture devices. They not only look at the hydraulics, they also look at how it clogs up. They put a test mixture of trash in there that has really been designed to clog up screens. Lots of thin pieces of paper, as well as cigarette butts and polystyrene. They also look at a scour. So when the system is full of trash and on leaves and everything, they also turn it up to 200% to see if you lose any of the material you captured, because a self-cleaning stormwater device is not a good idea. They also they do a bead test, and a bead test is for this neutrally buoyant component. So they get these beads that have different specific gravity. Half of them are above 1 in specific gravity, and half of them are below 1, and in a range roughly around 1. That's meant to be SG. So they kind of sit in the water column like the plastic for the diver. So they're testing it with these to try to make the test as real, true to life as what we see in the field. So that's screening and considerations, a good engineer has to think of when he's looking at different screening devices and the testing that's going on. And then we move into like separation. And we often get asked, how much suspended solids does your GPTs get? And that question's kind of a bit weird because it's not called a filter or a sediment capture device. It's called a gross pollutant trap. and they do capture sediment, and they can be used as pre-treatment, but they're not really capturing the fine material. And the fine material is the material that has more heavy metals, higher nutrients content, and the finer material is more bioavailable. The contaminants associated with the finer material is more bioavailable. It means it absorbs into marine life a lot easier, like settling in the sediment in the bottom of a stream. If it's really fine, it can release the heavy metal with a lack of oxygen and turn into dissolved heavy metals, which is easily absorbed. So yeah, it's they don't capture the fine material, which is really the toxic stuff. But so how does GPT remove sediment? Well, basically what I call teacup physics. If you put sediment you put a teaspoon of sugar in your cut tea and you give it a good spin, you'll find the sediment builds up into a nice little cone. And that's because the longer the flow path, the longer the time that piece of sugar is in there, the more likely it is to settle. If you take a bit of the energy, if you were pouring that sugar in from the top, or if you were just placing it in the teacup, the amount of how the energy of that sugar coming in, that will also influence whether it will settle very easily. We also at Stormwater 360 add in flow controls into our gross pollutant traps just to slow the water down so it can give a longer residence time inside the teacup so things can settle down. So flow controls are a useful tool when it comes to settling sediment in a gross pollutant trap. But when we're talking about settling sediment, a really big thing is that size matters, particle size that is. And the bigger the particle, the easier, the quicker it's going to settle. The fine particles, as I said, which are the more contaminated ones, the longer they're going to take to settle. And they might not even settle out inside a gross pollutant trap because some of those very, very fine particles literally take days or weeks to settle. So I've got here what we typically see. So there's two in lab testing, and I said there's a lot of lab testing going on in the USA. You take a synthetic stormwater sediment, and you have to kind of come up with what does that look like? What size particles are in stormwater? And historically in the past, they used to use a mixture called OK110, which is basically 110 micron particles, which is pretty fine. You know, we're talking 1/10 of a millimeter. And so that was the old test method. And a lot of devices have been tested with 110 micron, and we even have test data on 110 micron. But as things moved on and they wanted to make those lab tests more true to life and more like what we see, New Jersey and the Canadian ETV program, and even there is an ISO accreditation now, developed a test sediment like that's more representative. It goes down starts at 2 micron. This is a log scale. That's 1,000 there, and that's 1 down here. And it has it right the way through the range of particles. And this is kind of what we see in sediment. It has a D50 or a 50 micron, 50% of the particles are 75 micron or smaller or larger. And that's representative. But when we test a device with say OK110 and the New Jersey or NJ particle size, there's quite a difference in results. So I've got these two vials here on the right. This is New Jersey sediment mixed up at 5,000 milligrams per litre. And this is OK110 mixed up at 5,000 milligrams per litre. And hopefully this is going to start because if not, I'll do
If you
this.
select the pointer.
There we go. So here's probably just me talking for a while. Is it playing? Yeah, it is playing. So yeah, I talked over my intro to what those two are, but what I'm going to do is I'm going to pick them up and I'm going to give them a shake to show you how they settle. In these two bottles, we have synthetic stormwater mixed with water at the same concentration. The one on the left here is using OK110, which is a synthetic stormwater sediment that is approximately 100% is between 100 and 120 micron in size. On the right, we have the New Jersey and the Canadian ETV test sediment.
With this sediment, it has 20% below 20 micron, 50% below 75 micron, and 100% below 1 millimeter. So the New Jersey and ETV test sediment is more representative of what we see in stormwater. Many manufacturers have tested to 110 micron, and we will just show you the difference. So here is the OK110. You can see the sediment in the bottom here. And if I take it up, take it back and shake it, you can see the sediment swirling around in there and settling out. Now if I take the New Jersey sediment, which is roughly the same, and shake it up, you can see the stark contrast in the two settling, the sediment settling in the two. There's quite a difference there. So testing to the New Jersey test sediment is more indicative of what you will see in normal stormwater.
And then so next thing is, so how does that work for New Zealand, right? Okay, we're testing in a lab in America with it. Someone's told us this is representative stormwater, right? So I did the exercise of taking the New Jersey particle size, which is this, and then plotting it against some of the earlier research in Auckland on different particle sizes around Auckland. And you can see it's roughly similar. Maybe Auckland's got slightly finer particle size than the New Jersey one. But the whole point of testing in a lab like we're doing is just to benchmark the performance. Everyone's testing the same. And so then you can have a look at these devices. What's really the difference and how I can design them? But it's good to know that the New Jersey particle size is roughly similar to Auckland. So, but if we were using 110 and we were testing to 110, you know, and saying we got 80 or 90% of 110, well, 110 micron is only real is about the 70th percentile. So that's not really representative. It's only 30% of the sediment if we that we would see in a real situation if we test to 110. And what's even worse, if we compared that to Auckland, well, geez, that would only be something like 8% of what we're likely to see in Auckland. Now, some other people don't want to, they're quite aware, some other suppliers are quite aware that these are just gross pollutant traps or pre-treatment devices. So when they report their performance, they talk about a D50 of 150 or testing between 50 micron and 1000 micron. And that again is only really half the particle size we're likely to see. And that's appropriate if we're using it as a pre-treatment device. But if we're using it as a standalone device in a retrofit situation, we're not really considering half of the sediment coming in. So if someone says we get 60% with a 150 micron particle, they're really only getting 30%. So it's somewhat misleading. Another thing, really important thing to discuss, we've already mentioned that particle size affects the removal rates you're likely to get, but also the flow rate through the system affects the removal rate. Here's some test data from a vortex system. We have different particle sizes that we tested it to. The bottom one is 50 micron. The top one is 150 micron. And this is the operating rate. That's the area of the device divided by the flow going through it. And so at 27 litres per minute, we would get here, roughly about 45% removal of 50 micron, but nearly 95% removal of 150 micron. But as we go higher up in flow rates through the device, you see the performance drop off. Now at Stormwater 360, if you really want to make your gross pollutant trap remove more, we can design it to a lower flow rate and get higher removal rates. Or as we did in Christchurch and in the Black Rock in Christchurch on the Banks Peninsula, they had a really fine surrounding soils, really fine. So we designed the vortex there to more of a 50 micron particle rather than 100 or 110 micron particle, because they had fine surrounding soils. The system had to be bigger, but we were achieving better pre-treatment than just putting a standard off-the-shelf device. So talk to us about, what you want to do with your gross pollutant trap, because we can tune them to achieve different performances, or different removal rates. So, with the Vortex, because it's been around for so long, it's been pretty interesting. We've done a whole bunch of lab testing for New Jersey, and we did a whole bunch of field testing also for New Jersey. And it was really, really interesting. We did the lab testing first, or our partners did. And we got 64% removal with the New Jersey sediment. And we thought that's pretty good. That's pretty good result. When we went out into the field and tested it, we actually got 95% removal. And it was like, wow, geez, we should go get this approved by Auckland Council as a standalone device, because we only had to get 75% removal, and this device is getting 95%. Wow, it's great. But when we looked at it a little closer, the particle size was really coarse. It actually had a D50 of 500 micron. So we had boulders coming down the pipe, falling into the device. So it really wasn't a good measure of its performance. We could have gone on and said to everyone, this thing's amazing, it gets 95%, but that really wouldn't have done a lot for water quality. So we went in and we actually broke up the samples and we separated it out into a bunch of different, we kind of split it into different samples, and we analysed for the different particle size ranges in that stormwater. And what we found out is actually we're getting a really good result. We're on the less than 100 micron particles, we're getting 93% SSC. So SSC is a different way of measuring TSS. I won't dive into that, but it's it's a whole sample analysis, and it captures more of the heavier samples than, say, a TSS analysis. TSS is you take a pipette out and you subsample, and quite often you just get the lighter material in there, not the heavier material, because it settles so quickly, or denser rather than heavier. And it really throws out the question, which is better, lab or field testing? And I think they're both really good and they have their place. I think lab testing is very effective for measuring the performance of devices for solids, coarser solids, trash and debris, because you can control the test. You can put the same density of particles in, the same particle size, and you can see how it would work. You can change that test if you have a place that finer sediment and you want to see how it works with finer sediment. You can change the sediment if you had less dense sediment, such as, say, car tires. You can change that and you can test it to see how it goes. When you go out into the field, you kind of just get what you get. You can't change the feed in, and you need to look really hard at the field testing results to make sure they're not skewed by natural environmental factors. And what we see now overseas is a lot of people are going back to, a lot of different companies that come up with devices are going back to the same site someone else tested on, just because they know that they'll get a good result there. I think field testing is really important when you look at heavy metals and nutrients, because it's a very complex mechanisms going on in their removal and their transport. They transform with other contaminants. And when you're looking at them these more complex pollutants, I think you really need to field test to make sure that in a real life situation, you're achieving what you're achieving. It's very hard to do a lab test for nutrients and for heavy metals that's repeatable and representative of what you see in the real world. So I think they've both got their places. I typically think that lab testing definitely has a place for suspended solids and trash testing. But yeah, for more of the nastier pollutants, I think we want to look at field testing. Also, if we're looking at a pre-treatment device where it's not going to be the only device in a solution or in a treatment train, it's probably appropriate just to do a lab test. Now, another thing about the lab testing, I just mentioned that there is the scour testing. You can't really do this in the field because all of a sudden your device is resuspending and throwing out material that's captured, and you might not even notice that until you get your results back. You just suddenly see it's exporting rather than removing. And the lab test that you do in part of New Jersey and the Canadian testing which we've done with the EnviroBasin. Here's an EnviroBasin on a beautiful Canadian day. And this is the EnviroBasin being tested in a Canadian lab. What you do is you half fill the device with the test sediment. That's what the test sediment looks like. And then you put different flows through it. And these are surface loading rates. That's the flow over the settling area. And you lift it up to see how much is resuspended and thrown out. To give you an idea here, 200 litres per minute per metre squared on an EnviroBasin is roughly 1.2 litres a second, and 2,600 is roughly 15 something litres a second. So a catch pit or catch basin only takes about 20 litres a second. So we almost go up to the peak flow. And the standard is that you can't release any more than 20 milligrams a litre as an effluent. So you're putting clean water in and measuring what's going out. And you can see here the EnviroBasin had negligible resuspension. This is one of the big problems with catch pits and catch basins. They work really well in low flows, but as soon as you get a large flow, it just throws it back out. And we've got testing on a normal catch pit versus an enhanced catch pit or an EnviroBasin. So that's why lab testing and sediment kind of discussions. I'm really running out of time, so I'll just quickly zip through here now. So hydraulics, gross pollutant traps, they typically have a pipe that comes in and out at the same level. And what they do in order to create the volume and the energy to make the water spin or go through an orifice or go through a screen, they build up head. Now that needs to be allowed for in your network design. Some are permanently submerged as well, like this one on the right. So at Stormwater 360, when you come to us for a design, we'll come back to you with this is the water surface level upstream of our device, because we're going to have to back it up to make it swirl around and do its thing. So that's a really important thing to ask your supplier. What's the water surface level? Don't ask what the head loss is, because that's really dependent on your flow rate and your velocities going through the system. And if you would have attended the hydraulics course before, you can understand what I'm saying. So I'd ask people for what is the water surface level above my device. And when we look at the bypass, the hydraulics, it's really important to think about how we're going to handle the peak flows. There's operational hydraulics, so the water quality flow, which is usually about 1/10 of your peak flow. But what happens when you have a big storm event? You're 1 in 10. That's got quite a different head loss when a system is online to when it's offline. Often suppliers only give you a one number for a head loss. And it's like, well, is that operational flow or peak bypass flow? If really, when we put these devices in, because they back the water up, you really need to put gross pollutant traps offline. Putting them online is really going to cause you a lot of problems. There's two ways you can bypass a gross pollutant trap. It's either an orifice or a weir. Here's some examples. Here, this is an orifice. That's an orifice. This one's here is a weir. If it's a catch basin type device or at source, you really need to consider kind of clogging, or if it's internal bypass, you really just need to think, what happens if a piece of something gets stuck in there? Because if you half the cross-sectional area, you'll only get a quarter of the flow through the bypass. So you have to have a safety factor or a factor for clogging. But we really recommend placing it offline. And this is a picture of a vault capture. The bypass weir in the vault capture is this little line here. Now, by putting it offline, we can have a much longer weir. And that means the head losses are really controlled. If you've got really big flows and really shallow install, you just make that weir longer and you control all the head losses you want. Also, it prevents any resuspension and throwing of material out of the device once it's been caught. Now, quickly moving on, evaluation. Well, I've just given you a whole bunch of things to think about. What are you targeting? You're going to target plastics and trash, or you're going to target sediment, or you're going to target both? If you're targeting both, or you're targeting either one, you're going to think about how's that's going to be removed. Am I going to be separating it, or am I going to be screening it? You got to think about the operational hydraulics, how much it's going to back up at normal operational flows, or what are other bypass flows? What are you going to do with them, and how's that going to impact your network? with climate change, we do not want to get this wrong as stormwater engineers, because they're going to be looking for us when, you know, a carpet factory gets flooded out or something and we've approved the design. Moving on, and then if we're really wondering about the performance, I mentioned all these testing protocols. Well, most of the devices in New Zealand have passed overseas testing protocols. So you can go and look at these. Here's the, this is the New Jersey Department of Environmental Protection. So they've got theirs there, and you know, they don't go, well, we got 63% for that, for Technics in New Jersey. They go, look, they're all roughly the same. There's a lot of variation when we go to site. Let's just benchmark all gross pollutant traps at 50%. You know, we could split hairs over what one product got on one site versus another site, but it's really the site that's probably influencing the result you're seeing. In a lab test, you know, they're all being tested exactly the same. And also, there's a bit of a confusion in America. There's new NJCAT, which is the verification agency, and NJDEP, the Department of Environmental Protection. NJCAT is just, they just review the testing. And I could go get anything verified. I could take a paper bag and say, this is a paper bag. Can you make sure it's a paper bag? And they'll go tick. But it won't get approved by the state, because they have strict requirements and they review the data. So if you want an approval, I'd go to NJDEP. There's also the Washington one if you want to see field results. You can also write to Washington if you want and ask them for the full test report, and they will send it to you. You know, it's all public information when it's used for a city council or a government permit, so they happily send it to you. And then moving on, you also really want to consider the maintenance, you know, and this is another one that's often confused. People think, oh, that device is expensive, but they put it on a highly trafficked road and they designed it to be as small as possible with not very much storage area. So it's not really the fact that it was expensive device, it's because the access was limited. You know, it might have had a nursery with lots of topsoil, and they didn't account for all the sediment that was coming in, so it filled up. So it was more the site that was influencing it. When you do look at a device, you got to think whether it's hand maintainable or it needs a machine. And if it's hand maintainable, it's going to be definitely a lot cheaper. Like two people in a pickup truck is around about $500 a day, where a Vector truck with 2 operators is around about $500 an hour. So if you can hand maintain a device, it's definitely going to be cheaper. Then you've got to think about things like replacement parts and maintenance frequencies and the storage volume. You know, how big is that storage relevant to the catchment? If you have 100 hectares coming into a device that only has 3 cubic meters of storage, well, you're going to have to maintain that a lot, or not. It won't capture much. Lastly, safety is critical, and I shouldn't really put this last. I actually think I should probably put it first, but safety is a growing concern, and the cost of safety is well, it's, you know, it's unlimited cost. So you want to make sure that you don't have confined entry when you're installing a device or maintaining it. You need to be aware of sharps and illicits. You want to make sure the device is robust and doesn't break, because if it does, you could end up with flooding. So safety, you need to review that and talk it through in detail with your supplier. And then lastly, whole of life costs. And this is just a little snapshot. Sometimes it's a little bit counterintuitive. This is some work done by the California Water Board, their Los Angeles Water Board, and their work leading into their full trash capture work. They looked at whether they should put big end-of-line GPTs in the areas, because they had to retrofit trash control, or whether they would go maybe break it into lots of sub-catchments further up and put GPTs in there, manhole type GPTs up there, or whether they would go right to the source and do catch basin interventions. And over the whole of life cost, they found catch basins and the end of line devices, which is the bottom 2 lines, were roughly about the same cost. The inline or mid catchment ones were a lot more expensive. And to explain that, well, it was all good when you could go down the end of the catchment having one device that you would only need to maintain. You could afford to buy the piece of land and do that work. But if you went the other side of that, was with the catch basin technologies, you didn't have to do construction. And you could also really target your hotspot areas, the areas that you're likely to get a high trash loading. And the requirements there was to remove X amount of kilograms or pounds of trash each year, because that's from their background monitoring, that's what they assume the load was. So by targeting the hotspot areas, you're getting more bang for buck, essentially, especially if you didn't have to construct something. What they found was not effective was putting lots of GPTs in a catchment on small subcatchments. So that's why we taken a litter trap to the USA, because they've realized that hotspot targeting with catch pit devices that are easy to maintain is a good solution. So yeah, gone a little bit over time, 6 minutes or a lot more over time, but yeah, any of that information, if you want to know more about any of that stuff, we can definitely sit down and talk to you about it. And I'm opening it up for questions now, Matt.
Thanks very much, Mike. There's a lot to digest there, and a lot to digest, especially from the perspective that there's not the regulation and everything put in place in New Zealand. So we're still kind of trying to find our way. And I think that's probably where I wouldn't mind starting is, you know, there's not so much in terms of regulation around gross pollutants with New Zealand. So for those consultants that are designing to more strict outcomes and that have receiving environments that are requiring the inclusion of gross pollutant traps, how would you then look to benchmark and verify the performance of that device or of a proposed device in relation to including it within a treatment train?
Well, I think that's definitely the role of those verification and those testing protocols. As I said, they're all tested the same way, and they're all following tests that are designed to be as true to life as possible while repeatable. So I definitely would say don't listen to us. I'd say go to those websites, and we encourage people, look into them, look at those technologies. They have the test reports there. You can read them and you can understand them, and even reach out to those regulatory agencies overseas, because they're happy to share their information.
Fantastic. Shannon had a question around, the recommendation of bypass arrangements, which I think, Mike, you've covered in terms of both performance and hydraulics. Peter Mitchell had a very interesting comment as well around for delivery of maintenance requirements, which for Auckland Systems Management is key to good environmental outcomes, but the cost of providing maintenance on an asset like a motorway is a big consideration. Is that with an offline design, you can isolate the device to provide safe maintenance in a variety of weather conditions. But in addition to offline, what else is a consideration when you're kind of doing a feasibility study into the installation of a GPT, whether it's the depth of the network, pipe size, space, or even, the treatment flows?
Yeah, we didn't really dive into the design aspects, and that's a really important thing. Not all GPTs can fit in with site limitations or geographical limitations. Often that dictates which device you will select to use. A high water table, you don't, and a manhole system, you'll have to put extra, anti-buoyancy stuff to prevent it popping out of the ground. Or you might have a very flat area like Christchurch, and your depth to invert is really, really shallow, and some devices require a large volume to achieve the pollutant removal, where some doesn't. So you really need to talk to your suppliers and understand that depth to invert, how that works with the hydraulics, and then the depth below invert and the water table and all those factors. And we didn't really touch on that, but our team of designers can definitely, and consultants can definitely help you talk through all of those, the variables. We recommend a process of determine what you want to remove, then look at your constraints, then look at the products that you could possibly use or the solutions you could use.
And we have lastly a question from Aries in Botany, and something that I'd be definitely happy to come and have a chat to you about is in terms of for large sites where putting multiple treatment devices can be expensive, is talking about, do you first treat then detain, or detain and then treat? Which is a relatively simple one in our eyes.
Yeah, well, a detention device can be a pre-treatment device as well, because it will drop sediment out. Also, if you have a plastic bag, it's a good way to block up a detention system, really. Or if you're using a milk crate as a detention system, well, that's definitely going to block up with leaves and plastic bags. I say it's better to pre-treat before the detention system. Then if you pre-treat well, you can use the detention system, not that it's allowed by some councils, to hold back the flow and slowly go to your next stage treatment, your wetland or your filter or something like that as a next stage. So you're kind of not allowing bypass in that secondary device, and lowering the loading on it so it works better. Yeah, so I think you're better to pre-treat, and then you don't have to go in and clean out your tank or your detention device. But I've seen it both ways.
And it's certainly something that, Mike, as our technical director, has a wealth of in-house expertise for the likes of, talking with Arsini about really complicated sites at that level. But we've also got Kevin, who is our lead engineer, and also both myself and Vainant and Anton in the sales team were able to talk through. And if there is a large site that is particularly complicated that you do want to investigate something like this, we can have a chat about it and see, how we might be able to integrate and adapt what we have to fit in. And with that, thank you all very much. I think that is most of the question. There's a couple of other ones that will follow up afterwards. Thank you, Mike, for devoting your time between flying visits to America and to across the world looking at stormwater. And thank you all for joining us for this webinar on gross pollutant traps, performance evaluation and approvals.
Thanks, Matt. Cheers.